So, good afternoon again, ladies and gentlemen. So, now we have another exciting talk from Professor Kalyanmoy Deb. So, he's endowed chair professor at the Department of Electrical and Computer Engineering in Michigan State University. He also holds the professor position at the Department of Computer Science and Engineering, also at Michigan State University. Professor Deb's main research interests are genetic and evolutionary optimization algorithms and their application in optimization modeling and machine learning. He's largely known for his seminal research in developing and applying evolutionary multi-objective optimization. Prior to coming to MSU, he was holding an endowed chair laboratory position at IIT Kanpur in India. His computational optimization and innovation laboratory at Michigan State University continues to act in the same spirit. He has consulted with various industrial and software companies in the past. So Professor Deb was awarded the prestigious Emphasis Prize in 2012, TWAS Prize in Engineering Science in 2012, Mandami Prize in 2011, Boise National Fellowship in 2011, Distinguished Alumni Award from IIT Kanpur in 2011, Edgeworth Pareto Award in 2008, and several other awards. So recently he has been awarded an honorary doctorate from the University of Jyväskylä in Finland. His 2012 IEEE DEC NSGA2 paper is judged as the most highly cited paper and the current classified by Thomson Reuters having more than 14,000 citations. He's a fellow of IEEE and the International Society of Genetic and Evolutionary Computation. He's also written 2 textbooks on optimization and more than 400 international journal and conference papers with Drucker score citation of more than 70,000 with H-index of 87. So he's in the editorial board of 20 international journals. So let us welcome Professor Kalyanmoy Deb. Thank you.
Thank you, Marwan, for this opportunity to talk to all of you in the SBSE area. First of all, I have to admit that I don't 100% work in SBSE. Marwan has been responsible for me to get into this. But it's really wonderful and lots of complexities that these kinds of problems provide. So that's why I'm very much interested in this area. So what I've decided to do is give you an overview of what's going on in the area of evolutionary multi-criteria optimization. In short, we call this EMO. So I'll be sometimes referring to EMO instead of saying the whole name. And then some of the SBSE results. Some of the results students are already presenting since morning, and there will be some more, I think, in the next session. We also have quite a few papers on our website, which you can see. So all the results on SBSE, it really came from Marwan and his students, but both of us have been involved in planning the research. So I'm at the Department of Electrical and Computer Engineering at Michigan State, as Marwan has mentioned. Now I have established a lab called Computational Optimization and Innovation Laboratory, COIN, in short. So anything we work on, we put it up there for people to download. So if you like any of these topics that I'm going to be talking about, or you want to know details about them, you can visit and download the paper and come back to me if you have any questions. Okay, so the outline of my talk is basically talking about what is multi-objective optimization and where they are useful, what are the different ways to handle multiple objectives using classical methods. I just want to touch upon, because many of you may not know some of the methods that exist in the classical literature. then comes the point, why do you need another algorithm like evolutionary algorithm to solve these problems? And I'm going to show you one or two algorithms which are what many of you already know and heard. Probably is NSGA2, but we now have NSGA3, so I'm going to give you an idea of some of those advancements that are going on. There are basically three ways we are applying or finding rather EMO is useful in various problem-solving tasks. One is, of course, you want to solve the multi-objective problem, so you need to develop algorithms for that. Second is, there are some offshoots that are coming out now that EMO methods can be used for what is known as multi-objectivization, a problem that is not a multi-objective problem, but you can treat it like a multi-objective problem and solve it in a better way. So I'm going to show you at least some directions of what are those problems and how you can achieve better results instead of treating them as a single objective or some other way. And then, of course, this is getting a very important area, particularly when you go to practical problem solving. You cannot just find a number of optimal solutions that usually happens in a multi-objective optimization. You also have to tell people how to make decisions, how to choose one solution from it. So this is becoming a recent trend, particularly when you have very large number of objectives where visualization becomes difficult. I'm not going to talk much about this today because this is still an ongoing research, but I would hope to just provide you with some directions. Okay. So let's start with some negative issues because I got motivated by the morning talk. It's really good to see where we are before we say something, before we do or what we like, really. So when I go to industries, particularly meet practical people who are interested in maybe using any optimization method, maybe evolutionary algorithms as one of the optimization methods, oftentimes those that are a little gray hair, been working in the field for a long time, most of them will come and say, oh, optimization doesn't work in my area. So they like to avoid it most of the time. I'm sure those of you who are working with industries have very similar experiences. They have a different view of what they mean optimization versus today's world, what we mean optimization. Okay, so but the first impression or first kind of idea that they have of optimization is that they are not going to tell us anything good. We're going to spend some time, but eventually we won't be using them, we won't like them. So I try to think hard and figure out what is that difference. I think what they mean by optimization mostly is a single criterion optimization. Think of any design or any model or any process that you're trying to come up with, and you have one goal. So the goal could be, okay, I want to do it with minimum time or minimum cost involved in making that design. You can spend an optimization algorithm working on it for many hours. Eventually, you get a solution that has really found a very good solutions for the minimum cost. And once you look at the solution and you say, is that the one? I'm not going to use it because it doesn't do well in other contexts. So what this means is in practice, nobody is interested in one single criteria of arriving at anything. There's always more than one criteria. Cost versus quality, as we all know, right? When you go to market to buy something, you get something cheap, but you sometimes don't like it because the quality is not so good. So the solutions for one is not the solution for the other. And that's, I think, one of the key areas where we differ in the way we understand optimization versus the industry people who have got limited experience in using, they only think single objective optimization. And there are lots of softwares, optimization softwares, which can only do single objective optimization, so they don't have any other way of getting at any other solution. Other thing that's there is they look at the solution and say, this is so close to being feasible and infeasible that if some of my parameters are uncertain, or if some parameters have a slightly different value when I'm applying it, this solution will be infeasible. So when you really optimize the solution, you are lying at the brink of being feasible and infeasible. So that's another reason people in the industry don't like optimal solutions. Okay. But then we know how to handle those things. If you know some of the ideas or uncertainties, you can be away from those. If you know that this cost is not the only objective that you have to consider eventually, you can supply those other objectives that you want to include in the optimization task, and you can redo the whole thing. So that's where we're getting at. So we have basically have multiple considerations: cost, quality, functionalities, emission, environment. All these are important. Sometimes you have multiple loading conditions, operating conditions that a design or a solution has to go through. So you need to consider all these things, and then one design or one solution has to be considered for multiple different disciplines. It may not be so in SBSE, but then you can have different considerations that in order to come up with a particular problem-solving task under that. The bottom line is you cannot provide one single dollar value or one single criteria where there are different criteria or different functionalities that exist. So you cannot say that, okay, here is a combined objective. If you minimize that, that's the one I like all the time, right? So that's where the problem is. So if you're talking about the multiple objectives, you get into a scenario where there exist multiple optimal solutions. So here's an example I always give. If you're trying to buy a car, there are at least two criteria you're going through. One is the cost. You have to see your pocket. And then opposite to that is how much comfort or how much kind of safety or some other criteria that is opposite to the cost is for the car that you're going to buy. So you can get a car that is very cheap, but you don't achieve too much on the other objective. On the other hand, if you try to find a car that will maximize your comfort, you have to pay a lot of money, right? So that's the trade-off. Now the question is this an optimum, or that's not an optimum, or is this an optimum, that's not an optimum? So the answer is both are optimum, right? With respect to certain trade-offs, you have to now say which is more important to you, then I can tell you which is really optimum. So when you're trying to come up with different solutions, you may not have that information that which one is more important to me or which one is less important to me. Believe me, in practice, if you go and ask the designers or decision makers that, okay, you're saying cost and comfort, both are important, which one is more important? They're not going to answer it, right? Because it depends, it doesn't depend on them. It depends on some other set of stakeholders. Like in this case, the public who is going to go, the customers who are going to go and buy a car. It doesn't depend on the designer. Designer cannot dictate and say the cost is 2 times important to everybody to comfort and have just one car, right? It doesn't work that way. That's why we see a portfolio of car for every car manufacturer, one for different groups of people in the community. So that's how the multi-objective problems are solved. So when I was in Spain, before my talk at in the dinner table, I had the host and his wife was there, and so we're talking about shopping and all that. So she said, when they go for marketing, buying some stuff, dresses and stuff like that, they always go for these 3 B's, bueno, bonito, barato, which actually means good, nice, and cheap. And I immediately sensed that tomorrow I'm going to be talking about something that this is not possible. It's never possible to have a good product, a very nice product, and also cheap, right? You have to sacrifice one of them. So I said, okay, you may not want to come to my talk because you may not like what I'm going to say. But this is, then I realized is that this is what people desire. This is what people desire, that I would like to have such a car. If anybody can come up with a car which will satisfy all these or any product, obviously that's the best and people will go and buy. Which that means is that this boundary that I put here is non-existent. You can actually come over here because when you're moving up, you're increasing your comfort and you're reducing your cost. So if this solution exists, then there is no trade-off. And everybody, there will be just one car in the market and everybody will buy that. So every manufacturer will hope to have that, but unfortunately it's not possible because of constraints and all the functionalities that we desire, right? So we always get into this kind of a scenario where there exist multiple solutions. So if you're trying to solve these problems, there are 2 tasks. One is, how do I find a representative set of solutions? So I look at what are different options. And then a second task that will say, how do I choose one solution from this set, right? And this could vary from application to application, from person to person. And we see that happening. Somebody mentioned in the morning that you buy a mobile. It's the same situation. We try to buy a large screen as large as possible so we can do a lot of stuff with it, but then the battery life reduces. So trade-offs are everywhere, and that's why we see a set of solutions. We're just trying to formalize this for any kind of multi-objective problems, this issue. So if you're interested in finding now algorithmically those set of solutions, you need a definition. You need some kind of a definition of what you mean by an optimal solution under multiple objectives. That's where the definitions come in, but mathematically there are various ways to define it. I'm not going to go into the details of that, but in computing, we use this domination-based concept, which actually takes two solutions, x1 and x2, and you know what are the objective values of x1 and what are the objective values of x2, and you can go into a definition where it says, does x1 dominate x2? If these two conditions are satisfied, then x1 dominates x2, and you can then crank your algorithm to go somewhere towards this Pareto set, right? That set is known as the Pareto set. So, so these are possible to be done in order to evaluate two different solutions in a multi-objective scenario. Definitions exist, so we can actually say something about whether one is better than the other or not. So if you use that principle, and let's say that I have given you a set of solutions, okay? Let's say 6 solutions here in the context of two objectives, F1 and F2, and it doesn't matter whether you have to maximize one and minimize other, or both minimization, doesn't matter. That definition still works. Given a set of points, you can actually find out which solutions are non-dominated. So in this particular context, for example, 3, 5, and 6 are non-dominated, which means that out of the 6 points, nobody is better than 3, nobody is better than 5, and no other solution is better than 6 out of these 6 population members. But if you give me 1, I would say 3 is better than 1, because you see I'm maximizing F1, so 3 is better than 1 in F1. I'm minimizing F2, so 3 is better than 1 in F2. So 3 seems to be better than 1 in both F1 and F2, so I can say 3 dominates 1, 3 is better than 1. But there is nobody which says that 1 is better than 3, or 5, or 6. So that's why the 3, 5, and 6 belongs to a set. That's what we call as non-dominated set. So in a population of size n now, with n objectives, we need algorithms that will quickly find and say which are the non-dominated ones, because the ones that are non-dominated ones are my candidates, are the ones I want to push in order to have an algorithm move towards my actual Pareto form. So this stuff of picking out the non-dominated solutions in an algorithm we do very often. Every generation we do one. So we need very fast algorithm. Fortunately, there are fast algorithms available. For 2 and 3 objectives, you could do it with n log n, where is the number of points, where m is 2 and 3. But if m goes more than 3, the complexity increases slightly. The log n gets to the power n minus 2, but that's really not much. Now if you think of the whole search space, all possible points, and you apply this method on the n log n algorithm, and identify the non-dominated set, those are your Pareto optimal set. But we'll never be going to be using that algorithm because it's already more than the search space, the size of the search space, so we'll use a smart algorithm to find those, but for a population, we can still use this. The bottom line is, there's more than one solutions that are Pareto optimal, right? Okay, so moving on, how is this different from single objective? You've already seen is that in a single objective scenario, there is a search space where we are searching, our algorithm is going and searching, but there exists one objective function. So every solution has an objective value, another solution has another objective value, so we can compare these two values and decide which is better. Eventually we search here and get to the solution that has the smallest function value we can minimize it. When you have a multi-objective problem, 2 or more, you have the decision space or the search space where your algorithm is going to be searching for good solutions. But then each solution in your search space also maps to another space, which is called objective space, right? Because now you have a character of this space, there's F1 and F2. And this can have some geometry, and the Pareto optimality is defined here, right? So you need to now identify which points here, now a set of points here, that is going to give you an idea of this particular front here. So that's, if you're minimizing F1 and F2, this becomes the front. So all those points, when I look at where they're coming from this space, will give me the Pareto optimal front. So this set of points behaves like a front, looks like a front, it's called a Pareto optimal front, and this is called the efficient front. or efficient set. Okay? So we are after these solutions. But the bottom line here, the difference again, you see there are two spaces, and we need to still search in one of the spaces, but which solutions are important is defined in this space. And so your algorithm has to go back and forth between these two in order to arrive at those solutions. Now, if you look at the classical way of doing it, first what we have to do is take the problem and convert it into a single objective problem by using either weighted sum, or there are many, many other ways. They've been researching it, I mean, since 1970s, very early 70s. Lots of methods are there. How do you convert the multi-objective problem to a single objective problem? Obviously, you need to do some kind of parameterization, some kind of information about preferences, and all that should come in. But once you have done that, you can then use a single objective optimizer to find the solution corresponding to that. Then the question comes, once you find the solution, is that what I was looking for? If you say, no, I don't like this solution, you can go back and change your parameterization and convert the problem into another one and solve again, maybe you find another solution. So this method of generating one solution after the other by changing the parameterization is called the generation method. Okay, so that exists in the classical literature. That's the only way they can give you a set of solutions if you're unsure about your weights, about your parameterization. That's the only way you can change it. So you see that that kind of a process is repetitive every time you start with a different weight vector, and there is no parallel advantage that you get. When you're solving one, it's done. Then you are changing your problem. Problem means by changing these parameters. You have a new problem, and you have to solve it from scratch. No advantage you get from the previous solutions, previous problem that you solved, right? So there's no memory effect. So with the evolutionary idea, where you have a population of points, we hope to have that memory effect coming into play and solve this kind of problems quickly. Okay, so that was our hope in the beginning, and there exists lots of literature papers where we show these things again and again. So the weighted sum approach, what you do is you get to a point where the weights that you've chosen become tangent to your Pareto front. The problem with this is that if you have a non-convex Pareto front problem, where the problem is such that you have a non-convex front, then these non-convex area you're not able to find using the weighted sum approach. So they know that. So they have other approaches. They call one is, for example, epsilon constraint, where you convert it in a different way, the multi-objective problem to single objective in a different way. If you have two objectives, and you say, okay, one of them I'm going to use as objective, the other one I'm going to put as a constraint. So here, I can put f1 as a constraint, like f1 less than epsilon 1. And if I choose epsilon 1 here, f1 less than epsilon 1 means only this part is feasible now. Okay, and the original problem had the whole thing feasible. Now when you minimize f2, minimize your f2, you will get C, because this is your feasible region, so you will get C. So you see now the non-convex part, which was not possible before to be found by the weighted sum, now you can get them just by changing the epsilon. But the issue is, how do you know where to put the epsilon? If you put epsilon here, or anywhere there, or here, you are not going to get anything there, right? Either you get infeasible solutions if you put epsilon here, or same solution D again and again. So if your choice of epsilon is not good. And particularly, if you have higher number of objectives, like 5, 6 to 10 objectives, for 10 objectives, you have 9 such epsilons to deal with. So it's a very difficult proposition in order to get a good combinations of 9 different parameters to put in a region where you're interested in, right? So if you think that the problem lies with the classical methods is that they are treating multi-objective problem as a special case of a single objective problem, which is really anti-computing concept to me. Because in computing, one of the things we try to write a code that is generic, and then if it degenerates to a special case, the code should degenerate that way. Your parameter value if given in some way that the code should degenerate, it should do. You don't write a code for a special case and then hope that it's going to make it generic for an arbitrary case, right? So that's one of the problems to me. And then the second is that there is no parallel search. Okay, so here are some results from a very good algorithm taken from classical literature called normal constraint methods. If you have to code one method using classical method, this is the one I would recommend. So I'm not giving you the details of the algorithm, but I'm showing you some results that comes with it. there are three different problems. One has a convex, non-convex perimeter front and minimizing both objectives. And there is a part of the front that is called weak perimeter optimal set, which means one objective, they're exactly the same, other objective things vary. So sometimes you are interested in this set also, but most of the time for engineering practical purposes, we are not interested. So this algorithm is able to find some part of that and the whole front so nicely after 20,000 evaluations. Okay? Then you go to another problem which has lots of local perimeter front, like you have local optima and single objective, where you can have local fronts. Here is the global front that you can see just peeping up or peeping out here. But it got stuck over there, okay, after 100,000 evaluations. Here is a three objective problem where after 100,000 evaluations, this is the status of the population. So which means population is number of times you have used this. And some of them had reached, some of them did not. If I run some more number of evaluations, if I allow, then they will all go there. But this is the status. So this is where we are when you're trying to use one of the best methods that exist in the classical literature. I'll show you some results later on with our evolutionary method. But let's talk about that. What is an evolutionary method? So you all know evolutionary algorithm. Okay, it deals with starts with the population of points, and then they get recombined, mutated, and obviously selected, and then you go into that kind of iteration. So we are hoping that when you have a multi-objective problem, these evolutionary methods should give you a set of points on the perimeter front. Because we're dealing with the population, we can expect that population can line up on my perimeter front and give me an idea of the front. So that's the whole hope, actually. And then, of course, the decision making is still there. And that's how, as I said, most of the consumer industries are designing, and that's the philosophy they're using for that problem solving task. Okay. So, well, I don't have to, because all of you here are familiar with the evolutionary methods, so I probably can skip all that. Just want to show you that these evolutionary methods that we do, we get oftentimes we get criticized by classical researchers who do not like stochastic methods or a method that does not have a convergence proof. But some of the things to tell them back is that if I have an arbitrary even single objective optimization problem, there is no algorithm as a proof. So we are as good or as bad as any other algorithm, right? So if you have to solve those problems, which are nonlinear, that's a non-differentiable, we are as good or as bad as your method. Okay, so then let's look at it and see how these works. But if there is a problem that's differentiable, convex, which there is a provable algorithm using classical or whatever method, we should not try to solve those problems. Because there exist provable methods. So we should accept that and then see what kind of other problems we could do. Okay. Now here are some examples. This is a Shinkansen, that's the bullet train in Japan, was designed in 2006. It was in operation for 2007. The nose of this bullet train was designed using a genetic algorithm simply because the classical methods are failed. All the mean time tests that they have to do to have it acceptable. There is another one here, is a Kone's elevator. The deciding of which vehicle, which car will come to which floor when lots of people are going and putting their requests. Every half a second, a genetic algorithm is run, and the allocation schedule is made, and the cars goes to those floors. So you can see that landing annotation call here, I've taken it from the brochure. They are using genetic algorithms to solve it. Okay, so this has been there since 1995. So there are just two examples, but there are many, many other examples in the literature. Some of them they may not be able to tell you that they have used it because of restrictions, but I know personally lots of places, GA-based or evolutionary algorithm-based designs are out there. We've done some work, and some people also say that when you give a talk about GA, they say, how big a problem have you solved? Okay, that's a common question, because they're still not having the trust, whether they're useful or not. So we took a problem from industry, which came actually. It's a stochastic scheduling problem. So if you look at the problem, it's an integer linear program. So it's a linear program, but the only difficulty is every variable is an integer. So then comes the difficulty. If you didn't have the integer restriction, you could solve by a simplex search method, Tanzin's method, for example. You could do thousands, tens of thousands, even millions of variables that you can solve. But as soon as your variables become integer, you cannot use that method. So then you have to kind of have another core, another outside shell called the branch and bound or some other methods that exist. So that means you have to call those linear programming many, many times. And what happens, those kind of algorithm becomes exponentially expensive. We have tried on this problem. The company wanted us to solve a problem that requires about 15 to 20,000 variables. So 15 to 20,000 integers. Those who work in these areas, particularly in operations research, you can go and ask them that, have you solved an integer variable problem, maybe linear, with 15,000 or even 10,000 variables? They would scratch their head. It's a difficult problem for them to solve. So we bought a simplex solver, which is used for these kind of problems. And they have a way to handle integer variables, which is this exponential methods that I mentioned, branch and bound. We could not go beyond 500 to 1,000 variables. That too had to wait 7 hours, 8 hours to get a solution. Okay? So we couldn't have used them, that algorithm, and give to the company. So we customized. So again, there's an importance that the morning speaker talked about, is the need for customization. One algorithm will solve one problem idea. In optimization, you can forget. You have to customize. So we customized the method, and one genetic algorithm for solving this problem. I'm just showing you the final summary plot here. We took this problem. They are interested in about 20,000 here, but we took it from 100 to 1 million values. This is a problem which you can extend to any number of variables. Their problem with our customized GA is solving in 10 seconds, and each one of the points here has a 99.7% accuracy. So they're very, very good solutions. But we took it, so they're not interested beyond that. But for academic interest, we go up to a million variable integer problem, and we solve them in 30 minutes. If you look at a plot, if you believe that this is a good representative line for these points, it's polynomial. Then it says it's polynomial performance. Now, what we are not claiming is each of them being an optimum. We're saying they're very close to the optimum. Optimum can be somewhere from 99.7% to 100%. So we're very close, but we are not claiming they're optimum. This problem belongs to the class of knapsack problem. And there is no, it's an NP-hard problem, so there is no polynomial time algorithm for solving this. But see the difference, what I'm trying to highlight here. If you can accept an approximate solution like that, you can get a polynomial algorithm, which is very fast. It's like less than quadratic. The slope is 1.2. It's not even quadratic, between linear and quadratic. But if you said, no, I cannot live with anything optimal, then you have to spend this exponential amount of time. It's taking 30 minutes, the exponential would take 30 years to solve that. So now you decide that 0.3% that you left at most, is it worth waiting 30 years to get that solution or not? Or you are happy with this? So this is where the difference is between what these people in the industry I talked to you about feel about optimization. When they talk about optimization, they think I'm going to give them an algorithm that's always going to give me optimum. It's going to take forever. But if you can live with approximation, some of these methods, like evolutionary methods we're talking about, are excellent. They're so flexible, you can go and put your own stuff, put some problem information, customize it for the problem you're trying to solve. All right, so this 1 million variable problem has not been solved before, so that's news actually. So now getting back to the multi-objective scenario, when you're trying to solve this problem, there are two goals in your algorithm. First is that you need to converge to the parent form, right? And so you can't be like this, where you have a good diversity, but you have not converged. On the other hand, you can't be this set of yellow points where you have converged. All of them are converged to the parent form, but you don't have a good diversity. So you're not showing me different solutions. They're only iota different from each other. So I think we're looking for this black set of points here, which is well diverse, well converged. Right? So you need to then have these two goals. Convergence is an important operation in my algorithm, and also maintaining diversity of those points is another important goal. So usually in our single objective evolutionary methods, we don't have both these goals, but now we need to have. And then we have these niche preservation techniques to solve multimodal problems people have worked on in the context of evolutionary algorithm. So we borrow those ideas so that we can maintain diversity, and we keep reference to those non-dominated solutions, if you recall I showed you, so that will achieve the convergence. But the main thing that happens with the implicit parallelism is this. you are dealing with a population of points. If some of your points are progressing better than other parts, those points will now cross over with your other members and can pull those points towards them. So that's the advantage of parallelism in an evolutionary setup. And that's how you solve these problems much better with evolutionary methods than the one-by-one way of doing it. So there is a history of how we have come so far. It's all started around 1984 when this guy, Dave Schaefer, has did his thesis, developed this, what he called vector evaluated GA, but his thesis was negative. He said, okay, we cannot maintain a good set of points in the very front. It eventually goes to 100 points. There was a vacuum of ideas, but Goldberg in '89 suggested some ways of overcoming that problem. 3 groups of researchers have taken that clue and came up with different ways of implementing Goldberg's idea. Fortunately, everything worked. And that gave the world ideas of moving forward, and that was really the beginning. All these algorithms had 1 or more parameters to be tuned. The next generation algorithm, which I call elitist EMO, eliminated some of those have eliminated any parameters. So you still have the population size and crossover the standard BC parameters, but the fact that you're solving a multi-objective problem, it doesn't introduce any more parameters. So that's how it all started about 20 years ago. Okay. So here are these first generation algorithms. These 3 have been quite popular since then. You can look at the Google Scholar citations so far. They are pretty good, right? And then some of the applications like this one I'm going to show has also boosted and showed people how is this EMO ideas different from the classical multi-objective optimization. So here's a problem where you have to send a spacecraft from Earth to Mars. Okay? You need to decide on a schedule when to launch, and then what would be the path. So basically, you're doing it for 2 different objectives. First is you want to go there as quickly as possible. Turns out if you want to go as quickly as possible, you have to take a lot of fuel, but you cannot take too many people or apparatus or something like that. So your goal also is the second objective, which is opposite to the first one. It says, I want to maximize the mass delivered at the target. It looks like they're in conflict. So when they used my NSGA, the first generation method, they came up with this front. Okay, so you see the trade-off. This solution 44 shown here is the quickest possible way you can get there. Okay, and it tells you everything, when to launch, the dates, where from, what will be the path, and everything you see. The bottom line is about a year to get there, and about 700 kilos you can deliver at the destination plan. If I take another solution from the front, which is here, you take 1 more year. So 1 year, and this is about 2 years to go there. But now you can take about 160 kilos more. So that's the trade-off. Okay? If your mission requires that certain mass to be taken, you have to wait. And it tells you how. And there are many other intermediate solutions. You cannot wait 1 more year. If you can wait 6 months, it tells you how much more mass you can take. Because these are all optimal results, right? But let's now extend our thought and go to 72, which is over here. That's 1 more year from 73. And you take only 2 kilos more than 73. That anybody can tell. It's not worth waiting 1 more year just to be able to take 2 kilos more. Right? So the fact is that now that you're seeing the whole front, you can see where to make your decision, where are the interesting trade-offs and where are not. If you did not find the whole front and used a classical weighted sum or epsilon constraint, your epsilon could have been here and you would have found this solution. And you would have never known you made such a bad decision. Right? So these kind of studies where you're finding a set of points before you make a decision, before you choose one, picked up from some of these examples. Because there's always some learning part that you have, and you're making better decisions by knowing what are other alternatives that are possible. I will show you some more advantages of doing this kind of work. Then came the second generation algorithms. NSGA2 is one of them. And look at the citations now. These kinds of work has really given this whole field a big boost, and people have been using. That's why there are citations. There's no other reason. Okay, so this is a little bit about NSGA2, some facts, and a lot of software companies have implemented it. I'm not going to really show you how the algorithm works because you can always find it in the literature. Now, here's the tricky part. I need to see if I can make it work. Okay, so here is the initial population. look at how the algorithm works with generations and comes towards the Pareto form of test problem. Because in this problem, we know where the front is. And you saw that how it came from a random set of points with iterations and converged as a front to this entire area. So you have actually different trade-off solutions at the end of your run. So for another problem, it may work slightly in a different manner, but that's how you get towards this set. So it finds a multiple set of points, not just one point, a multiple points, but not one point. So here are those three problems again that I showed you with normal constraint method. We did not change NSGA2, just the same population size, same other parameters, just change the problem and show you how they work. Here was the problem where, remember, we had a weak set of Pareto points which are usually not desired. NSGA2 doesn't find them. So you see after 20,000, same number of evaluations, this is NSGA2 result. And this was the result from the classical method. This was the result from the classical method on the other problem where lots of local fronts. Here was the front starting at 1 here and going all the way. This is NSGA2 result. So we actually converge to that global Pareto front. Because of the evolutionary algorithms running in the background, it has the ability to avoid local optima and get towards the global optima. So that's the advantage you get with the same number of evaluations. Remember this side I showed you a 3 objective problem where there's a Pareto surface now, but this normal constraint method did not go all the way, and NSGA2 now comes and converges to the whole front in 100,000 evaluations, and it shows you a nice distribution of this Pareto front. You still see some gaps and all that. This is because of the NSGA2's grounding distance operator. I will show you now NSGA3, where we see a much better distribution of the same problem. But this is how it all started. This idea, again, has been used in many industries, as I said, including one called the MapTech now. They do mine scheduling in Australia. And the company's from Australia, but they're actually solving problems. I was involved with this. They started with 3 persons company to all the way now 50% company and recently bought by MapTech. They started in 2008, and we're talking about 2014 when they're bought by this company. It's a huge company now with evolutionary algorithm in their core program. Okay? Churning out schedules, having millions of variables in their problem. Again, none of these solutions we are claiming to be optimal. This is something that beats all the existing softwares that exist in this literature, and that's all we are caring for, right? When you're trying to do something new. Can I get something better than what we have? Now, when you're developing or working in such areas, you need to be able to evaluate the performance of an algorithm. There are many different performance measures. These are the ones you will be hearing more and more in the literature. It's called hypervolume attainment surfaces. Hypervolume simply gives an idea of both convergence and diversity. It doesn't do a very good job, but there doesn't exist really too many good performance measures. So here is the one that actually computes the net area dominated by the set of points, and this area then is called the hypervolume. So when you have a larger hypervolume, you have gone much closer to the front. So that's one metric which kind of does a job of giving you a combined idea, but obviously you cannot be perfect with that. Attainment surface method is one that's actually takes care of multiple runs when you're doing it GA or a NEMO algorithm. You get multiple runs. Each run gives you an attainment surface, and then it does some kind of statistical analysis to tell you where is the 50th percentile line, where is the 100th percentile line, and so on and so forth. So these are some statistical methods. So as I said, lots of work we have done, Marwan and I and his students. So here is one with NSGA2 applied for model merging. You have different models parallelly developed, and now you want to merge them into one. You could think of multiple objectives there because you want to minimize the number of desirable refactorings and maximize the number of important enable refactorings, and you can expect some kind of conflict. As long as you choose 2 such conflicting goals, you are ready to get some kind of Pareto solution, right? So we applied to 7 different open source systems, which some of you I've seen in the morning also using. You can get into a Pareto front like this. These are 2 objectives, one being minimized, the other being maximized. And sometimes you get a Pareto front that looks like that, with a point that seems to be an inflection point. On one side of it, there is one kind of slope, another side of it, another kind of slope. So there is a natural preference for those kind of inflection points in your Pareto front if it exists. It may not exist. For example, if you look at this, although we mark this as a knee point, it's quite small. But here and here, you can see them bulging out. And those are actually the preferred points, which are called knee points. So one thing is to choose which point, and the knee points can be your preferred points when you're choosing one point. But if you just want to get these different solutions to get an idea of what's going on, then the points are there for you to see what they are. So if you take some of these points and see with another algorithm, which is also multi-objective, how this is doing, in these 7 systems that we worked on, in all cases we get hypervolume that is higher than the other one. And as I just told you, higher hypervolume means better performance. It has come much closer to the parity farm. So there's something going on in NSGA2 that makes it better than some of the other competitors that we have when you have two or three objectives. Of course, in higher objectives, it doesn't do as well, but I'll show you another extension of NSGA2 to handle higher number of objectives. But let me talk few things along the way, some of the advantages. One thing is, of course, as you're seeing, solving a problem with single objective versus solving a problem with multi-objective, you suddenly get more information because multiple solutions come in. You can either use those information to gather knowledge and also for the decision making for choosing one, right? So there are both aspects here. But there are more things you could do. One that is called as multi-objectivization, which I mentioned, that you can use this concept to solve otherwise a single objective problem as a multi-objective problem. And there are advantages you can get. One of these offshoots of that is called innovization, which you have again used in the context of SBSE. It's discovery of vital information from a set of points. So in the interest of time, I'm going to skip the multi-objectivization aspect, this aspect, but I'm going to talk about innovization. So what is innovization? When you do a multi-objective optimization, as I said, you get a Pareto set, right? You get a set of solutions. Here, a design problem where I have minimizing the size of the design of the motor here and maximizing the power gives me this set, this Pareto set. Now, one thing is this, okay, I've got the set and then I have to choose one for my implementation, fine. The other thing is for gathering knowledge, what I can do is I can now look at what are these different solutions, what are their variables, how they are changing when I line them up from small size to large size. What are the variables that are changing? That might give us some useful design principles, some kind of patterns or anti-patterns that you're talking about in SBSE, right? So here's an example of the same motor design problem where there are 50 variables were there, but we fixed 45 of them to certain values. We just wanted to see the principle here working all right. And only changed 5 of those variables. And we found this Pareto set. There are 200 motors here. We observed that out of the 5 variables, 4 of them are exactly the same. And they are kind of mentioned here. So all these solutions are changing with respect to just one of the variables. So these are the kind of design principles that you can get out of it once you find the Pareto set and figure out what is common and what is not. We tried this in many different areas. One is this team selection. Okay, so this is not engineering problem. This is now a problem where it's a game of cricket, which is really very popular in India, Australia, UK, and some of the Commonwealth countries. Right now, there's a final going on in Australia, so I'm staying awake most of the nights. So the time difference is really very popular. So what happens is there's an 11-player team. Okay, so there are lots of players that are available. Their statistics are known, and now as a team manager, you have to form a team. There are a lot of restrictions. You cannot have more than 4 foreign players, 1 wicket-keeper. There are different things you got to have. Okay, so we are maintaining all those rules. Now our goal is, this particular game is like baseball, because there are 2 parts of this game. One is the batting score, and one is the bowling score. And you have to do well in both those scores. So we said, okay, we have to maximize the batting average, we have to minimize the bowling average. Let's do a bi-objective minimization and form teams. Each dot here is a set of 11 players that form the team. And we are playing it on a computer to see how is this team's batting average and how is this team's bowling average. And you see this nice Pareto form, right? And the year we did this, I think 2010, and this Gen 9 Super Scheme, this was the team that won that year. And what I'm showing you is that all the player statistics were taken from that team, and we find the bowling and batting average. We have at least here 20, 30 different teams that beat that team that won that year. So we're saying if you're playing on a computer, we have got better teams. And now what happens in actual practice is a different thing, right? But what this says is we are capable of finding good designs or good kind of teams. But I'm not saying that is the focus of this research. I'm saying we've got about 100 different teams. If we now look at all these teams and do this innovation, that means 11 players, 11 players, 11 players. I want to see which all players are common. Now it can give me some information about the contribution of which player into what. We notice that there are 129 player tests that we have taken. All these player teams here, only 29 of them are present. 100 of them do not even appear. Any one of them don't even appear in any of these teams. So this is one of the ways you can filter out the good players when you look at both aspects of this game and try to find a better one. Because these solutions are pretty good solutions, right? So this kind of innovation idea can be used for various different purposes. We also tried this for games, playing, for example, tic-tac-toe, and came up with this Pareto set, which maximizing the number of wins and minimizing the number of draws, and putting a constraint that we should never lose. We come up with some very nice concepts of strategies of playing the game that will outperform other strategies. So these are some extra benefits that you get by using a multi-objective optimization in your work. Sometimes you want to not just optimize by explore the designs, you just want to see what are different solutions that are possible. Okay, so you can use these methods. For example, here is one result where we are designing trusses over, like a bridge over a river. Okay, and then our goal is to minimize the weight. Just one, and this again goes back to my first slide, saying what the industry people think versus what we think are optimization. They think this way: one objective optimization. Every solution, this is a whole population of my GA, looks very much the same. At this point, there's not much variability left. I don't get too much information other than this kind of trapezium kind of bridge. That's it, right? But I come and say, all right, I'm going to now make it really interesting. And I say, okay, this gave me a very good design. Maybe that's the best design. I introduce another objective to my bi-objective optimization. I still have this objective to minimize. Second objective is, I want to make any design different from this design. So a population member that is more different from this, better is the fitness, the second fitness. Okay? So that means I'm introducing some kind of diversity. And look at what happens at the end of the run. There are all kinds of interesting designs now present. And so here I'm not saying I'm going to choose that or this or that, but it just gives me different possibilities that are there for me to then do further things. So just for design exploration purposes, you could use that. You could also use that to improve your weight minimization by that process, but let me not get into that. With the little time that I have, let me talk about a few of the things that I mentioned that I will do already. For example, many objective optimization, and maybe some other robust optimization, stuff like that, okay? So I'll leave, this is decision making. I'm going to leave it for now for how to choose solutions. But let's go to many objective optimization because many of you will be interested in doing that for more than 2 or 3 objectives, which we call now as many objective optimization. The issue here is that when you have 2 or 3 objectives, people are now calling them as many objective. And when you have more than 3 objectives, we are calling them as, sorry, multi-objective, 2 and 3, and when more than 3, we call it as many objective. This is just terminology that's been accepted now in the Mo community. I don't particularly like this, but this is how it is. Now, okay, so but there are some issues when you are trying to use these multi-objective algorithms like NSGA2, SPA2, to problems that have more than 3 objectives. That's a 5 objective, 10 objectives. There are certain issues. The main issue is the large fraction of the population gets dominated when you're trying to use the domination principle. So they don't really work that well. It slows down quite a bit. So we came up with NSGA3. There are 1 or 2 other methods now, some other variants of that. We've said that we need to help the algorithm because we're trying to deal with a large dimensional space. So the way we help it is that we provide some kind of guidance lines. And these guidance lines are adaptive. As you are running, they get changed, okay, automatically. And then what you're saying in an algorithm is that go and find a point along each of these lines, but go all the way to the very front. Now that I've distributed the lines in the whole space, if the algorithm can parallelly go and give me 1 point for each of these lines on the very front, I have actually got the divergent diversity as well as the convergence is achieved, right? It's easy to say like this, but to really make it an algorithm that will scale up to large number of objectives with different scaling in the objective values is not an easy task. But so I'm skipping a lot of stuff. And I really, if you're interested, I urge you to look into the paper and see what we've done. But these are some results. Remember, I showed you the results from 3 objective problem with NSGA. There were some gaps here and there, but look at what we can achieve now. Very nice distribution of points. If you want only a few points, you don't need 50, 60 points. You want just few, 10 points or something, we can give you such a thing. If you have constraints, we can work with constraints. If you want only a part of the font, you're not interested in the whole font. If you say, give me some points in the intermediate part of the paradigm, because that's where interesting trade-offs going on. So it can go and give you that. Or you say, I have 15 objectives. There is a 10 objective problem. I have 10 objective problem. And this is one of the ways to show called PCP, parallel coordinate plots. This actually tells you've got a pretty good distribution in 10-dimensional space. I can't show you 10-dimensional surface like this. So this is one of the accepted ways of showing higher dimensional fronts. Here is a practical problem called water, where there are 5 objectives, and you can see number of solutions having trade-offs. Okay, so we've used that to software engineering as well, particularly for the refactoring purposes. I don't have to tell you all these things, you all know that. But what we have done is in this particular paper, going to Aperitos, we've got 15 different objectives that's been considered and applied to these 7 different systems that we mentioned. And there are different refractory types that we have considered in it. And it's a sequence of all that you're trying to optimize with these under 15 different objectives. Here is this 15 objective PCP plot that you see, which actually says that there are all kinds of trade-off points that we found. So here there may be about 100 or 200 different solutions that we have. Obviously, one thing you can do is you need to choose 1 or 2 of them for implementation, and that's where decision making has to come in. The other idea would be, what have I learned? What is common in all these 100 solutions that I have? So all this stuff we can do. And when we gather all this and summarize our results, what we see is in all these 7 different systems, we get a distinct advantage of these NSGA results in terms of number of port smells that we fixed. With the other methods, which are mono-objective methods, the other 2 colors, could not do so many fix-ups. Okay? So these are some advantages that you get when you deal with larger number of objectives. Okay, so I'm going to skip now some of these things, but this is to say that when you have uncertainty in your problem, you need to, instead of finding the Pareto front, you may be interested in finding the robust front, which means every point on that Pareto front is now insensitive to the parameter fluctuations or variations. And in software engineering, we have lots of uncertainties. And so this work actually presented in Gecko last year actually shows that this robust frontier that has been found here, these 3 different systems that we're showing here. And then when you have low uncertainty level, medium uncertainty level, and high uncertainty level, you can then find a bi-objective front in this particular case. We worked on, and the lead points are very clear from some of them. This could be used for final implementation of these ideas. Okay, so there are lots of advancements that are going on in the context of multiple objectives. One of the things that we're getting more and more interested in is called bi-level optimization. This one has very little work, even in the context of classical optimization, but this is very, very practical. Many problems in practice work in levels, for example, stackable games. So there is one level, the upper level users are more prominent than the lower level players, and you get into an optimization problem which looks like that. There are going to be multiple objectives at the upper level, but a feasible solution at the upper level has to be one of the optimum of a lower level optimization problem. So it's a nested optimization, one optimization inside another. Obviously, this one is more has more priority than the other one. Then, because they're nested, you end up spending a lot of time solving them. So they're usually computationally expensive. Classical literature is really very naive in those matters. They just discretize, get a few solutions for the lower level. So we've been showing that this is another problem area where evolutionary methods are very good at. It's really incomparable to classical. So classical methods are not as good. So again, this needs time for me to go into the details, but just I'm showing you some pictures to get your interest in it. is that these are challenging problems, let me tell you. To understand even what is a Pareto front in these cases, you need to spend some time. So we came up with bi-level EMO algorithms, which actually is an extension of NSGA2 for 2 and 3 objectives, but those ideas exist now, so one can use. And we have actually used it for this test problem and also for code smell detection. Again, TOSEM paper to appear soon, where at the upper level we are actually minimizing the coverage of code smell examples, and then at the lower level we are saying that can we maximize what are the code smells that could not cover at the upper level. So there's a conflicting thing that comes in here, and this one drives the whole search, but this one goes and finishes the job. Just gives another level of information to the upper level. So problems can be split up like this, 2 different levels, and if you put them under this framework, then you can get some results much better than other results like the precision metric and recall metric. Both metrics, we have better results with the block method. That is our technique compared to the other known algorithms. So because of time, I really want you to go into, if you're interested, and look into some of these papers that are going to appear pretty soon. There are codes available for NSGA2. NSGA3, unfortunately, there is no code available, but pretty soon I'm sure it will be available. But the paper is out there, and it's an extension of NSGA2, so you can start. I think Maroon students have taken 1 week to extend NSGA2 to NSGA3, so it's possible to do. There are a lot of software companies that have NSGA2 as a partner. So you can actually start, if you're already using some of these, you can use NSGA2 from there, or you can think of acquiring one and do it. So I think it's a bright future in this, and it's able to solve lots of problems in a different way, giving you a lot more information that otherwise single objective optimization can do. So we are actually developing more efficient EMO algorithms, visualization of the frontier. When you go to 10 objectives, 15 objectives, we solved recently a problem from New Zealand. It's a land use management problem with 14 objectives. So one of the issues come in how to visualize this 14 objective space. We're still working on it, but there are some methodologies we have already developed. I'm not going to go into the details here. Decision making becomes an important, that's closely related to visualization. I mentioned bi-level. We already talked about some multi-level stuff that you can do. You will try level and other higher levels if you have to. How do you find near optimal EMO? Not just the optimum, like I said, because of this casting problem that I showed you, you can move very fast to get there. Does it happen also in EMO? Can we make it to the Pareto front very quickly, rather than finding the whole optimal front? How can we use distributed computing or cloud computing, all these parallel computing environments that are available today, to distribute the work of finding the whole front among multiple processors? So we've done some work, but these are some recent stuff that are coming in. Problems are expensive to compute, so meta modeling method should come in EMO. There's really not much work in this area. So how do you do it? One simple idea is to meta model every objective function, every constraint, but that is really expensive. Some other efficient methods are needed. I'm very optimistic about the whole thing. I'm already suggesting evolutionary massive objective optimization, but we have evolutionary mono, evolutionary multi, evolutionary many we already have, and now we're saying evolutionary massive to deal with 50 plus objectives. And believe me, there exist problems. Actually, there are problems with infinite objectives, okay, but we're not interested in those at this point. But do we need completely different kind of algorithms when we have such a large number of objectives? Fortunately, all of them to be is EMO. Okay, so that's under the same umbrella we can do all that. But then EMO for dynamic combinatorial problems, how can you combine EMO with some classical, if you have a local search, fast method using other means, how can you do that? And interesting applications. Okay, here's some a couple of slides I want to show. Here is some idea of the distributed computing. So if you have 3 processors, you can find a part of the whole Pareto front in one processor, and then you can collect all this information and you get the whole front. So this is one of the ways you can use parallel computing in multi-objective optimizations. Recently, we've done some more based on theory of optimality, which comes one of the ways comes is optimality conditions, where we're showing that this is the result from LSGA2 on a problem called ZTT1. I'm showing here that with generations, I'm running NSGA2, which does not use any derivative or any optimality condition, which uses selection crossover mutation. But all the non-dominated points, I'm computing a proximity measure that we have derived from the Keketi conditions. And the condition says that if that proximity measure is 0, then you are on the Pareto form. There is no other way you can be on the Pareto form. Look at what happens with the NSGA2 results. Starting with large value, with generations, it takes about 80 generations, and every point is on the true Pareto optimal form. So without using any gradient or any optimality conditions, we're showing experimentally again that when we run NSGA2, every point goes to the theoretical optimum. So these are some ways to gain confidence from our colleagues from other fields like classical methods that there's something interesting going on in our algorithms that takes us to the theoretical optimum solution. So these are very interesting kind of work to support this kind of things. Okay, so well, I've said so many things, but basically it's a fast-growing field. As you see, it's kind of expanding in many different ways. Practical applications, when you're willing to solve, then it gets more interesting and more ideas come in. We are diversifying and combining with other areas like decision making and mathematical optimization. Commercial softwares are available for people to use. So there's an all-round activity going on, both with the practice as well as theory. So welcome to the field. Thank you very much.
Many thanks, Kalyan, for this great. So we have around 10 minutes for questions. Yes.
Yeah.
Visualization.
Yeah.
Because I used to project multi-dimensional space into three-dimensional space.
Yeah. So unfortunately, I don't have anything today to tell you or to show you that. But we are working on different methods, different techniques to visualize. Only thing that's available now in which we borrow from the classical literature is PCP, it's parallel coordinate. But as you know, it doesn't make a very good idea to trade off. But there are other ways to represent it. You have to get it down to 2-dimensional, 3-dimensional plots. But we have ideas of using virtual reality techniques to visualize, and those are the things we are developing at this point. So you could do, and then there are some techniques where you could do some. Where is this noise coming from? Okay, there's nothing to do with that. So there are some other mathematical techniques that are available to analyze higher dimensional data, look into their lower dimensional manifolds, and see what is changing in that lower dimensional manifolds. So there could be that you have these 1,000 different points that you found using an EMO, but most of them follow certain patterns. Okay, so you can extrapolate. So you can hide all that information. Just look at those that are abruptly changing, those that are phase changer, rather. So can we identify those by going into the details of their lower dimensional manifolds and identifying those? So it's still fuzzy at this point, but we are developing methodologies for those things. So I think this is one of the areas I put that as a future research, and we have to spend some time doing it. But that will always be an issue. But I have hopes because of the virtual reality, the other kind of sensory stuff that you could do rather than just visualization could be the way forward.
Other questions? Yes.
Yeah. For the example you mentioned about making the team, suppose we want to have a big project, national project,
Yeah.
and we want to pick up the team for the research project. So can we apply?
Yeah. So this was a similar question asked to me in one of the presentation I made, and there was a professor I know. He always had about 30, 40 PhD students, about 10 postdocs, huge group. He works in chemistry. So he was sitting and he asked me, can I use your method to form my team, research team? And I think it's more feasible in those kinds of problems because you have the resume of every person in your team. and you have some applicants, you know their resume, you know their positive and negative things. So if you use such a thing, you can fill up overall portfolio of your team that you need. You can actually fill up and get a good idea of which persons you put together in your team, so that you have an overall good portfolio. So definitely possible.
Yeah, actually, in software engineering, we have a similar problem to the crowdsourcing. So
yeah,
crowdsourcing.
Yes, so
maybe monthly objective.
Right. So what I'm saying is even more, right? When you're doing this portfolio, any of these things, you are getting a set of, when you do it for two conflicting goals, you can always do it, that your size is the same, but you're saying, how much money do I have to spend, and what would be my output? Okay, so let's say you can have some other, and they're in conflict, you know that. Right? So, but once you get this different Pareto trade-off teams that you have, you can then look at what are the key players that are always ahead in my team. Those are the ones you want to maybe pay a bit more and keep them, right? You don't want to lose them. So it can give you a bit more information when you do such portfolio analysis and do the innovation study.
Any other question?
Yes.
Okay, thank you for this talk. So I have a question about multi-objectivization. So you need to go from single objective to multi-objective, or from many objectives to...
No, you have a problem, if I can get back, let me see. You have a problem here that is single objective to start with, let's say. But somehow you have difficulty solving it. So one example could be, if I just go here. Here. So this is a problem for constraint optimization. That means it's a problem having one objective function, fx, I want to minimize, and there are certain constraints I have to satisfy. Okay? So from all those constraints, I got one function that I call as a constraint violation. Now I'm saying that this one objective problem, I'm going to convert it to a two objective problem. One is to minimize my fx, that was my original goal, and also minimize my constraint violation. Okay? So then you get a Pareto front, okay? And this is my target solution, because this makes my constraint violation 0, and this tells me that this is the minimum fx. So that's my target optimal solution. This lies on the Pareto front, but only on one side. So what I'll do, if I treat this as a two objective problem now and use NSGA2 and focus my search here on this part, not the entire front. I'm not interested in these points. I'm interested here. I have a much better and quicker chance of getting there because of the flexibility in my search now. I have not added fx and cvx with some kind of penalty parameter. Look at what happens. These are best algorithms known to do well on these very difficult test problems that are out there in the literature. And these are the function evaluations, total number of evaluations needed to this optimum with some accuracy. And look at what we get using this multi-objectivization. An order of magnitude less. That's because we have opened up the search, made it very flexible. Okay, so this is what I mean, that a problem that is otherwise difficult to solve, like single objective, but somehow you think of introducing another objective, maybe two more objectives to make it flexible, so you can solve it better. There are many such examples, like floating in GP. GP, when you do genetic programming, one of the problem is the program sizes grow as you run, and everything slows down. A lot of junk is inside. So if you then say, okay, I'm going to have my original objective, and I also minimize the size of the program as a secondary objective. Now, those bloating will not happen because minimizing size is a goal, is an objective here.
Okay, so multi-objectivization, the goal is to convert single objective to multi-objective and better results.
Right. It should help you. Otherwise, you should abandon that because that's the way you have done this didn't work. So you have to think of some other ways to do it.
Okay, so also, I think before NSGA3, so people try also to multi-objectivize their optimization problems because they have an algorithm that deal with many objectives. So in the other sense, so do you think that the results...
That would be more like single objectivization of a multi-objective problem. But I'm not very hopeful about that because that way you're making your problem more constrained artificially, and then it depends on how you constrain it. But here we're doing the other way. We're making it open so that search becomes flexible. Yeah, so, yeah.
Other questions?
Yes, so I have one question maybe about, because when we try to apply multi-object, many objective in real-world software engineering problems, software engineers, they found most of the time difficulties to express their preferences in terms of values. For example, for them, 0.9 or 0.92, it's not a big difference.
Yeah.
So, so the selection of the solution based on the preference, just using like the formalization of that, and then maybe it will not work to select.
No, you don't want to use those techniques. So there are again lots of methods that are available. I categorize them into three: a priori, a posteriori, and interactive. Of course, this is my ultimate. This would be the ultimate way of doing it. Interactive method. I have one slide here that shows that. But a priori is you are deciding before is what you're saying. I'm not recommending that. Okay. So these are some a priori methods. But a posteriori methods, what you can use. Once you find the set of points, you can say, okay, what is one of my reference points? Reference point means some kind of aspiration point. So I'm looking for a car that will cost me, let's say, 20,000 rupees. Sorry, dollars, not rupees. In dollars, and that's a 75% comfort level. There may not exist one because you are too optimistic, right? You want to pay less and also have high comfort, but that's your wish. You can go and put that point here somewhere, right? So cost so much and comfort so much. You can put that. Obviously, this will be this white region because there doesn't exist a solution. Now you go and say which point from my Pareto font is closest to that. That's saying that okay, I have a wish. I know this is not possible to achieve, but what is the next possible thing that I can? So these are some ways the decision makers can provide their information and also pick a solution that is feasible. So you'll not be picking up these solutions, although these are Pareto optimal because your wish was not there, right? So it will go and find the one. So this is one way of doing it. They're called compromise programming. There are other things, marginal rate of return. If you don't have any preference, you say, I don't know how your front is, but these are all trade-off solutions. For each point, I will go to my neighboring points and look at the trade-off. That means to get a unit, to sacrifice a unit amount in one of the objectives, how much gain I'm making. So to make a sacrifice of this much, from here to there if I go, to make a sacrifice of this much, how much gain I'm making. Again here, to make a sacrifice of this much, how much gain I'm making. So if I take a gain by sacrifice ratio on both and take an average, and then I look at see for each point I have that gain by sacrifice ratio, give me a point that does that maximum. So that says that I am at a point where going to my neighboring points, I have to sacrifice a whole lot to have a small gain. So I'm not interested in moving out from there. So that's my choice. So that is more geometric way of getting it if you don't have any preference. So there are many, many such things that exist. Instead of saying, give me which one is more important to me, F1 is more important or F2, usually decision makers can't give you that kind of overall information. But it could be point-based, you have a target base, you have a target that you provide, you go and look for that. But I think the interactive one is finally, I recommend, is what it says is that you start with the emo, and after, let's say, 10, 20 generations, you show what are your time bound points. Maybe you filter it down to 3 or 4 points, show it to the decision maker, and ask them to make a pairwise comparison. Like here is one. So I've got 5 designs at some point I've got. These are the objective values. I'm minimizing both. And I'm asking the decision maker to do a pairwise comparison. Solution 1 with solution 2. Can you tell me which is better? I'm not asking you to tell the objectives which are better. I'm saying, is this solution you think better or that? Okay, some of the cases the person can say something. Yes, I like this more than that. Some of the cases when you say 1 with 4, they're so far away, they might say, no, I cannot tell you. And that's also an information. So I gather all that information and I model the decision maker with mathematical function like this. So I'm actually solving another optimization problem with this feedback and finding a mathematical ranking function that obeys, that follows the ranking that was given. In this case, he said 1 is better than 2, 2 is better than 3, 3 is better than 4, 4 is better than 5. That's what he said. Now, what function is going to achieve that? So I optimize and find this function. So now I can use this function information from then on in my NSGA2, incorporate that preference information and go and find more preferred solutions that the person would like. If he's a rational decision maker, By that I mean, it doesn't change his mind along the way. It will eventually take him to the point on the Pareto front that he likes, because he's been driving it, right? But come here at middle point and he changed his mind completely, because something he would have said here, he said completely different. Algorithm will get confused. So we have some results in our paper where we're going to simulate those things. How much deviation the person can be, still we can detect. But if it's too much, then that algorithm is confused and goes to the wrong place. So there are all these things possible, even to extend higher numbers of
Another question?
Yeah.
Regarding your explanation, the posterior approach, we are talking about gain and sacrifice.
Right.
So, for example, now I have 15 objectives like a software engineer.
Oh yeah, you can do
Now
that.
maybe I have to gain maybe 4 or 5 objectives. With few objectives, I make one.
That's a good point, but you can define what do you mean by gain by sacrifice, because some of them you're gaining, some of them you're sacrificing. You can take the least gain versus maximum sacrifice to be really pessimistic. You could do that. Or you could do average gain versus average sacrifice in all the objectives and come up with a metric. Come up with a metric that says something about gain versus sacrifice when you go from one point to a neighboring point. And then you're saying, give me that point from your set which really maximizes my gain versus the sacrifice I have. So that means, sorry, the other way, it minimizes the gain by the sacrifice, because that way saying that I don't have motivation because the gain I get is too low compared to the sacrifices I'm making to get out of that point. Or there can be some other criteria you can form from these gain sacrifice values. So this would be totally geometric. It would depend on the shape of the front, which you don't know beforehand. So that's why you cannot provide a reference information beforehand unless you find. And that's why I'm calling it a posteriori. You can only do it after you found the front. Or if you have some a priori knowledge of saying, this is my aspiration level, give me something close to it, then I will go with the second approach, the reference point based approach. But these are just two. There are other approaches like light beam, satisficing trade-off concepts. There are all these concepts that are worked on in the MCBM literature. We can use those, bring those ideas here in EMO, and come up with this decision-making thing. But a posteriori is what I recommend. But if you can do the interactive, that way you're quicker. And the other advantage of the interactive is that the decision maker is involved in your optimization process. And that's a human thing. If you go to your boss, if you're doing this and showing it to him at the end saying, this is the Pareto front I found, choose one, the guy will always doubt that. How do you get these things? Are there anything better possible? But if you're involving the person right from the beginning, the person thinks he played a role in that process, there is more acceptability at the end. Okay, so this is a psychological thing, but there's a lot of reasons to do interactive.
How well you visualize the prompt?
Yeah, visualization is the key thing when you go to more than 3 objectives. I cannot even show you like this, right? So as I said, that's something we need to work on. But that, to me, that should not be a deterrent, because we could do a lot of stuff in the background and then come up with something that looks interesting from that background analysis and get there. So those are some interesting areas to look into. Visualization is definitely on the top of my list. Yeah.
Okay, so there is no other questions. So let's thank the speaker.
Thank you very much.
So there is a break of 20 minutes. Then next session.
Oh yeah, now it's fine.